is assume, when you start assuming either charge or voltage, typically charge, we're going to ultimately use this relationship. So if we assume charge, then we get voltage, and we see the actual capacitance is Q over V. You all follow me on this, class? Everybody with me on this? It's just like the resistance calculations. We have to assume something. So we start by assuming Q. And what I'm going to do is put the positive Q at the center. And with a capacitor, the charge is always symmetrically distributed. If you put a plus Q on the inner surface, the outer surface will have a minus Q. It has to, all right? So I'm going to just put a plus Q on the inner surface, uniformly distributed around where A is. So now the next thing I'm going to get is the D field. And this is the way, the progression. Now, you remember how did we always calculate D field if we had a highly symmetric problem? There was one law we used. Do you remember? Gauss's law. We know that the integral of what? D dot ds over that surface is the charge enclosed. So for this problem, if I have my imaginary Gaussian surface at some distance r, and I know, do you all agree with me here that D field's radially outward by arguments of symmetry? Then I could say that the integral of D dot ds over that closed surface is equal to the charge enclosed, which I've arbitrarily said was Q. And the integral of D dot ds is always the D field's magnitude, right, times the surface area of a sphere. What's the surface area of a sphere of radius r? 4 pi r squared. I try to get you to repeat it because, believe it or not, usually audibly saying something will help you remember. Now, I'm not a psychologist, but in the military, I've learned one thing, that they try to get you to see, hear, and if possible, taste everything as often as possible because you'll remember them. Things of importance. So this is going to be 4 pi r squared equals Q. And therefore, the D field in the radial direction is equal to Q over 4 pi r squared. And it's in the AR direction. Do we all agree on that, class? Just show of hands. You all remember this, right? If you do, gotta make sure. So I got the D field. Q over 4 pi r squared AR. That's not too hard. Now, after you get D, the next thing you do is get E. So if I have D, right, how do I get E? Isn't it just D over epsilon, class? Right? Here I made it epsilon relative, so total epsilon is epsilon naught times epsilon relative. And now I have this equal to Q over 4 pi epsilon naught, epsilon relative, whatever it is, r squared AR. Y'all follow me? So I go Q, D, and E. The final step is getting V. And just like a resistance problem, the voltage will always be positive between the plates. You can't have look, the magnitude is positive. It's the difference in voltage that goes into this equation right here. Not positive or negative. You follow me on this? Capacitors is strictly positive. If it isn't, we got a bigger problem. Because that means you could have negative energy, which is not going to happen. All right. So I have that, and how do you get the voltage always? Integral of E dot dl, correct, class? Now I didn't put any limits there, but I know I'm going from the inner to the outer radius, right? And I might as well put an absolute value because I know it's got to be strict positive. So for that case, I'd be integrating Q over 4 pi epsilon naught epsilon r AR divided by r squared, and then it's dotted into DL, which would be AR dr. Now I've got to say one thing. That's DL, AR dr. It could have, I could add the other terms. I could say it's R d theta, A theta plus R sine theta, A phi, but the reason I don't, and I think it's evident to everybody, is that AR dot product will only be 1 when it dots into the AR component of DL. The other two components it dots into that, they're 0. Do y'all follow me? And so I'm going to go from, in this case, I go from A to B, put an absolute value on that. That means I have Q over 4 pi epsilon naught epsilon R. And then you get what? 1 over R squared integrated is minus 1 over R, correct, class? I'm putting an absolute value there so I know the result's positive once it's evaluated at the limits. So this would make this 1 over A minus 1 over B. Because A is the inner, B is the outer, therefore this would be a positive term. Do y'all agree with me? All right, now that's the voltage. Finally, to get the capacitance, I simply take the charge and divide it by the voltage. Now, this is where, just by looking, you see really what I'm going to do is remove that value of Q and invert this. Do y'all see this? When I see the capacitance is equal to Q over V, that's going to be Q over that Q, 4 pi epsilon relative epsilon naught, 1 over A minus 1 over B. And that means the Q's cancel, so I get 4 pi epsilon relative epsilon naught, and then it's over the quantity 1 over A minus 1 over B. I have a comment here about prior mistakes. Do y'all see that? That would be the capacitance of that spherical capacitor. Everybody agree with me here? It's not hard to see if you just focus. It's very clear. Okay. Now, you see this 1 over A minus 1 over B in the denominator. What I will see on exams, I'll see people somehow take this and make this equal to, which it's not, 4 pi epsilon relative epsilon naught, and they'll just put 1 over A minus 1 over B. Somehow they get that. It's not that. Y'all follow me on that, class? They will do it somehow. There's something weird about this where the mind doesn't work at times. And they'll do that. This is not right. This is right. Now, something that's always true with capacitance. Capacitance is always proportional to epsilon relative. You see how epsilon relative epsilon naught, or really I should say epsilon, occurs in the numerator? All right, it's never proportional to 1 over epsilon relative of the material, the dielectric materials. That's always true. As a matter of fact, one thing that becomes apparent is if we have this geometry with inner radius A, outer radius B, if we want to double the capacitance but don't want to change these dimensions, we just find a material that has twice epsilon relative. Do y'all follow me on that, class? And that's really important to appreciate the fact. Now I got to tell you, I think I mentioned this before, but I want to mention it again. In the age we live in, there are terms called supercapacitors. Have you heard these? How many have heard of that? You nodded your head. Supercapacitors are things that can store phenomenal amounts of energy in small volumes, and they can discharge that. Now, what they're really talking about is something with enormously large epsilon relative. That's a material science kind of problem. They have to have a dielectric that can stretch a long way without hitting some limits of stretching. So there can't be an arc over or anything like that. And then release that energy back into the system. Remember I told you these little dipoles stretch and store energy? Well, I'm not a specialist on this, and I don't want to talk outside my area of expertise, but I can say this. When you're talking about dielectric constants that are near 40, 50,000, typical up to 10 is 10 is about the upper limit on most common dielectrics where you have a breakdown strength that's reasonable. Then you're talking about stuff that is beyond standard material science and stuff that I've had. This stuff is exotic, and it probably has to do with materials that are engineered with like carbon nanotube technologies and things like this, and I don't know that, but I'm just going to say this. The place that they're really used right now, how many have had to start a car on a cold day and it didn't start? Anybody? Well, it was my life when I was young. All the time up north. When it gets around anything, I've been in 25 below zero once in my life. When you crank a battery, even a new battery almost, nothing. Well, the problem is the battery's power goes way down. The ability to draw current as temperature goes down. There's a lot of reasons for it. And it also goes down when it goes way up because there's internal resistance that goes up. There's a sweet spot area, right? But those capacitors, supercapacitors, don't care. So suppose I charge one of these supercapacitors up parallel to the battery with 12 volts. Now I'm ready to turn my car engine. What's the big deal with the car engine? I have to have a lot of current, right? Tons of current. Well, that has no problem discharging in cold weather. It doesn't have a problem discharging in hot weather. And it can discharge all that charge that it's stored very easily and supply the additional current it needs to get your car going. So that's where they're used now that I know of. Is anybody else familiar with this? They are calling them supercapacitors, and that's exactly what they are, but they're starting capacitors. That's what they're amounting to, some of them. What they'd like to do, and I don't think they're going to do it, but you know, I've been proven wrong before. They would like to have a capacitor that could store so much energy it could replace, say, a lithium-ion battery. Y'all follow me? That battery is just the storage device. That's it. But lithium-ion batteries can store right now 10 orders of magnitude what a standard capacitor can for the same size of energy. 10 orders of magnitude. Think about it. They're trying to get it to something that's reasonable because a capacitor, the nice thing about a capacitor is it never goes bad. You can discharge it. I mean, it does go bad if you break down the dielectric, but normal capacitors under normal use will not go down. They won't break down in your lifetime. Normal. I'm saying that with cautiously because electrolytics will. They do have basically a goo in there that will start breaking down over time. Anyway, I'm giving you something to think about in terms of your future and maybe areas you want to get into. If you want to get into stuff like that, the automotive industry has got an open door for you because they're very interested in this. Okay, that's the first thing I want to do with capacitors. We'll talk about energy too. But I want to do another one. I want to see how you work this with me. So this is the normal way you should do it. Doesn't have to be this way, but it's usually the easiest with the exception of the planar case. Usually you assume Q, get D, get E, get V, and finally get C is equal to Q over V. That's the normal way to do it. Y'all with me? If we do a cylinder next, I want just work with me on this. Suppose this question is worth $1,000 today. I have an inner radius A, outer radius B, and I have a dielectric epsilon relative inside between A and B, and I'm going to charge those things. I can put a battery out here. Assume the inner surface is metallized and the outer surface is metallized. Make the height of this thing just H. So I've done this all in terms of arbitrary dimensions. This dimension is going to be B. And I want to know the capacitance between these two cylinder walls. Y'all got a visual idea on that, what it looks like? Two hollow cylinders, and there's some dielectric material. So the capacitance is here, right? It's really between the inner and outer surface. When I gave that resistance problem for home harmony on the quiz, people were trying to get the resistance of current flowing along the axis, but I wanted to resist the radial resistance. That's the big difference. Make sure you understand what we're talking about. This is the capacitance between the inner and outer radius, and I'm trying to show it like this. Can you all visualize this? So now, anyone, help me out here. What did I do last time? Starting with.
Assume Q.
I assume Q. So I'm going to assume Q, and I'm going to assume it's uniformly distributed. I'm going to say it's uniformly distributed around the inner surface. On inner surface. Okay, now follow me on this one. It's all on the inner surface here, right? You could go ahead and calculate the surface charge density, but you don't need to. And I want you to listen to this. We know if I come out a distance, rho, that's greater than A and less than B. You all visualizing that? Now I know if I'm at a distance, rho greater than A, less than B, I know for a fact that the integral of d dot ds over that closed surface has to be the charge enclosed, right? Y'all follow me in this class? Now listen, it's not hard. If I'm out here, I have a cylinder surface like that that's concentric with the two. It looks the same, it's just between them. How much total charge is between them? Well, it's Q, right? That's the total charge it would be enclosing. The D field is radially outward, so there is no D field going up or down that I have to worry about the integration at the top or bottom of that surface. Do y'all follow me, class? So that's the Q I assume. Well, what is D dot ds? Well, it would be the surface right here of that cylinder. Do y'all see that? All right, so what's the surface of that cylinder? The way I always like to think of it, well, it's the perimeter of the cylinder, or the circumference times the height, isn't it? What is the circumference of a cylinder? 2 pi rho, isn't it? Isn't that the length around there, right? Times the height, correct, class? Times the height times d rho. That means, well, I called it d rho. So d rho, d in the radial direction, would be equal to q over 2 pi, pardon me, 2 pi rho a rho. And I'll just make this d. Does everybody agree with that? Times h downstairs. Sorry about that. Agree, class? If I made h equal 1, it would be easy. Do y'all agree with that, the D field? Now make sure you know what the D field is for these things, for cylinders and for spheres. This one, you can see it's 1 over 2 pi rho, right? And it's times Q on top over H. Q over H is like the line charge density, if you think about it, charge per height, right? So now we assume Q. Now I have D equal to Q over, and I can call it Q over H if I want. Divided by 2 pi rho, a rho. Now I need E. How do I get E? Right, divide by epsilon. And remember, epsilon could be a function of radial distance. This is the one thing you keep in the back of your mind. It could be a function of the radial distance. So that means it's Q over H divided by 2 pi rho epsilon relative epsilon naught a rho. And finally, I need V, which is the integral of E dot dl. Okay, and we know it's going to be strict positive, right? So what's that going to be? Well, I've got to integrate that from A to B of Q over H, and then you have 2 pi rho epsilon relative epsilon naught a rho. And what's dl in cylindrical coordinates? Do you remember the differential length? There's only one portion I care about. It's going to be d rho a rho, right? That's the first part. I could put the two other parts, which are going to be what? Rho d phi a phi plus, and this is just dz az But why don't those last two parts matter based on what we talked about a second ago? When you dot the A row into these two terms, it's 0. This will always go away and this goes away. And only this term will survive. I'm making a strong point of that because I'll see mistakes on tests if I don't. So that means I'm left with this integration right here, and all this goes away. All right, so what is that going to be? V equals what? I have Q, right, over H over 2 pi epsilon relative epsilon naught. What's the integral of 1 over rho d rho? People?
No.
Natural log, right? Not log basic, natural log of rho, but it's evaluated from B to A, or it's natural log of B over A. So that's the voltage. And therefore, for this system, what is the capacitance? I'll put it up here. Well, it's Q over V, or you can see really, I invert that and get rid of Q, don't I, class? What can't you read? You all follow me? It's B over A. It's after you integrate it and get log of rho, you have to evaluate between the upper and lower limit. You all follow me, guys? All right, and that means the capacitance here is Q over V, or really just flip that whole thing. And you get this equal to 2 pi, right? Epsilon relative, epsilon naught, right? And then it's divided by the natural log of B over A. I have a comment here, 1 second. And actually, you know, you should scold me about this, but somewhere, yeah, I forgot that H. It's also going to be times H here, right? Because I forgot the H here. And y'all follow me? It's there. I'm sorry, but I forgot it there. My bad. So I put it in. It's proportional to H, or the height, or the length of the thing. Thank you. Now, this one, take a look at, and try to glean this from this. Try to just make sure you appreciate it. Again, it checks the box. It's proportional to epsilon. It has to be directly proportional to epsilon. If it's not, you've made a terrible error. It's also proportional to the length. The longer that is, think of parallel capacitors. If you have H and I double H, what I've basically done is put another capacitor in parallel. It is exactly proportional to H. Y'all follow me on that? It checks that box, sanity check. It's inversely proportional to the natural log of B over A. Now what happens if B becomes A, or approaches that? The natural log of 1 is 0. 1 over 0 is infinite, right? If you have B approaching A, the capacitance is approaching infinity. This is something that you have to be aware of with capacitors. The closer the two plates are to each other, the greater the capacitance. If all other things are held constant, if you just have two pieces of aluminum, square pieces of aluminum, if you bring them closer and closer, eventually the capacitance goes to infinity. So you're saying, well, why not make them microns apart? Maybe angstroms apart, right? Anybody got an idea why you don't do that? Just your gut.
Don't have a dielectric.
Breakdown voltage. Here's the deal. You can only have so large an electric field before things go bad in a hurry. You've seen lightning, right? Lightning is basically an electrical arc over or breakdown of the atmosphere. So what do you think the breakdown voltage is inside this room? What kind of a voltage difference between 1 meter would it take before all of a sudden you get a flash over, you get arcing? Anybody?
50,000 volts.
3 million volts per meter. 3 million volts per meter. Now, you think that seems like a lot. Well, yes and no. Because we will learn that when you get filaments of conductors, you know, you all see thin wire copper, right? Filaments of conductors get something where you get field enhancement on the tip. So even though the difference between 2 points may be 1,000 volts, the field enhancement of that tip may cause an electric field value to be something of about 300 to 400 times what it would be just by taking the voltage difference divided by the distance. Could be a lot more than that. So you can get breakdown initiated by that, and as soon as it starts, it's almost impossible to stop if there's enough charge behind the system. And I gotta just say one other thing now. I'm trying to give you, one thing they try to tell us when teaching. Tell them examples in the real world that the things you're teaching apply to, all right? This is capacitance, here's capacitance gone wrong in a big way. So I worked on a railgun. We built railguns here. I mean, not for the military, just experimental railguns to prove we could do it. And we tested, we shot them over a mile a second, which is amazing to me because that's 5,280 feet, right? The 30-06 shoots about, what, 3,000 feet per second. We're shooting a lot faster than a lot of guns. It was just a small mass, but it really was impressive. Well, you know, the only way you do that is you get capacitors and charge them up. So we had these capacitors that were filled with oil, they were dielectric, and we have to charge them up at 10,000 to 10,000 volts. Now 10,000 volts doesn't seem like a lot, until you realize that now you have these thin pieces of copper sometimes coming off of these things. And as soon as you see the tip of one of these things glowing, you know what say Elmo's fire is? You ever heard that term, anybody? It's a glow discharge that happens at the tips right before the big event, when you know you wish you weren't there event, basically. And I remember the stuff we had to do to prevent that. We have to basically take all sorts of, I call it goo. It was really just, if you've ever done a Bondo job on a car, anything like that, you basically have something that's called potty material that's a very good insulator, and you got it anywhere there might be any kind of a frayed thing like that. And I remember this too, also seeing something about the dangers of, do y'all know what electrolytic capacitors are? I don't know if everyone taught this to you. There's certain capacitors you can only charge a certain way. If you try to have true AC current, they'll blow up because the dielectrics will start flipping. Remember those little molecules? Instead of being in the same direction all the time, they'll try to rotate and they'll generate a tremendous amount of thermal heat and they blow up. Well, and I was glad I didn't do this, but somebody didn't have proper circuit protection, and when they discharged the system, well, there's an inductance in the cabling that keeps the current going, and it ran the current through the capacitor, so it was developing a charge in the opposite polarity that it should be, and the thing blew up and looked like a grenade went off down it. I mean, honestly, these are huge capacitors, and when they blow up, to heat some of those things to get to blow up, it's kind of scary. I wasn't there, but that's just something about capacitors to be aware of. So the breakdown strength is the reason they don't make them that short. And there's this happy medium. Well, what can you get away with? And that's where the materials come in, because a lot of materials you use, like mica for the dial. How many, you know what mica is? Mica is used for most of these small little or ceramic capacitors like that. It's a pretty good insulator. I actually don't know the breakdown strength, but it's probably about 8 to 10 times air. So 30 million volts per meter type of thing. That's pretty good. It's lightweight. It's not bad. But what they're shooting for is something that could have even a much higher breakdown strength with a dielectric. Mica's only what, 4? I don't know. It's anywhere between 2 and 10 is typical for good dielectrics. If you get anything over 10, you start to have other problems, typically because you get losses involved with it. But they're looking for something with a very large dielectric constant that has a very large breakdown strength, and the two are against each other, because the higher the breakdown strength, usually the lower the dielectric constant, unfortunately. So these are things to be aware of. If you get a job in this industry, keep this in the back of your mind. Some of the things with capacitors you have to be aware of. All right, that's cylindrical. Now, question. Try this whole problem in your minds doing one thing different. I'm not going to let epsilon relative be a constant. What if I did what I did with that resistor problem? What if I made epsilon relative be equal to like 5 over rho? Okay, now how does the problem change?
Changes your interval from E to V, right?
This is epsilon relative, right? The dimensions of the problem don't change, do they? Where does this go in? Does D change, class? D is a function of charge, right? And the actual geometry of the problem. But what happens? Right, you all see that? Now all of a sudden if I put it in, this becomes what? 5 over rho epsilon naught, right? Y'all follow me? What happens there? Rho's cancel. Now the electric field is a constant, right? Follow me on this? Big change. All of a sudden the electric field's a constant. Now just continue, finish the problem. All right? Now what happens to the voltage? If the E field's a constant, what's the voltage? Well, it's normally E dot dl, integrated, right? Do you need to integrate anything there technically? Well, in a sense you do. You have to dot it in with d rho, a rho, right? But it's really just going to be that electric field divided by, or multiplied by what? The difference in A and B, right? So now it's going to be that field. It's Q over H, and it's over 10 pi epsilon naught, but then it's B minus A, or the difference in distances, right? Y'all follow me on that? And now, what is the capacitance going to be? It's still always what? It's always Q over V, right, guys? It's always Q over V. So when I divide these two, what do I get? I get 10 pi epsilon naught, right? And it's going to be times H divided by B minus A. Y'all follow me? Now, believe it or not, that simple problem I showed you will give you trouble on an exam if you're not confident with your understanding of how to solve these problems. I promise you, I looked at that resistance problem and it troubled me. I mean, there are a lot of people who got it right, but when I saw certain answers, it just troubled me that you either don't read the question carefully or you have a fundamental lack of understanding. So this is really important, guys, all right? Make sure you understand that. That's the capacitance. It checks the boxes, right? It's proportional to epsilon, well, for epsilon naught in this case. And what? As the distances between the plates, B and A, approach each other, it goes to infinity. Y'all see that? Because it's 1 over B minus A. Okay. The final one I'm going to do is the easiest in a sense, but it's the planar one. This is the one I don't generally assume Q. I can do it that way, but I go backwards. I assume V and get E, and then from E I get D, and from D I get rho S, and I get Q, and then I get the capacitance. So I go backwards on this one, but you don't have to. So this is the plate, the parallel plate capacitor. So here you have 2 parallel plates, both with area A. And actually, let me try to draw that a little bit better. And the distance between this is H. I'm going to say between them it has a dielectric epsilon relative. And I'm going to do this. I'll put a plus to minus voltage V naught on here. So you've got 2 plates with a separation of H. Both of these plates are surface area A. Now, what I'm going to say is that H is much, much less than the dimensions of these plates. So if these plates have a dimension L, I'm going to say H is much, much less than L. And by doing that, what I'm really doing is assuming these things can be looked at as infinite planes. Do y'all follow me on that, class? If they couldn't be, this isn't exactly true, but if they couldn't be, this problem would be much, much harder. So if I do that, here I assume V first. So that's my first assumption, V naught, right? Now, my second assumption, if you look here, I better put an axis in. Let's say this is the z-axis. Bless you. Vertical, and call this the origin right here. So if that's the z-axis, I want you to follow me on this. That's V naught. We can ground this part right here, call it 0 volts. Do you all agree with that, class? The upper part? And if that's 0 volts, right there, now I'm going to get E. Well, again, we're assuming an infinite kind of, these things look like infinite plates. So E would be V naught over H, and it would be in the AZ direction. Can you all see that? I've got V naught is the voltage difference, right, over the length H. E field is volts per meter. Take volts divided by meters. Now you got volts per meter. Do y'all agree with me there? How many understand that right there? Good? All right, now after you get E, I get D. Right? And what is D in terms of E? Epsilon E, isn't it, class? So now I can say that the D field is just equal to epsilon times V naught over H. I think he did this in your physics classes, AZ. That's the D field. We're doing this one backwards. Now once you have the D field, can you get charge? Well, you can get charge density. Now, I don't remember how I talked about this, or if I talked about it, but I'm about to. If you have a perfect conductor, anytime you have a perfect conductor, think metal, think copper, think something like that. Then the normal D field, D normal, is equal to the surface charge density. I can prove that by doing Gauss's law, or basically just putting a pillbox around there, but just trust me on this field. The D field, normal to the surface, is rho s. How many remember that or knew that before? 1, 2, 3. All right. Remember that always, because there can't be a tangent field on a good conductor. The conductor shorts it out. Follow me? The only thing you have is a normal field, and D normal will always be the charge density. So that means when I have this, it is the normal component on the surfaces, right? And that means my rho s is equal to D normal, is equal to epsilon V naught over H times AZ. And that's at the top and the bottom surface. Now remember, that's a surface charge density. But now to get the total charge, what do? If I have the density of charge and I want the total amount of charge, standard way is integrate rho s over the surface area, right? But rho s is a constant, so can't I just multiply it by the surface area? Sure. To get Q on one plate, it would be rho s times A. That would be epsilon V naught over H, right there. That's the charge density, and it's just times A, the magnitude of rho s. And that's this will go away. And then finally, to get capacitance, I take Q over V, and here, Q's right there over V. It just means capacitance is epsilon A over H. Do y'all follow me on that? Now, this is for a parallel plate capacitor. This is one you probably should know because of your physics courses. But remember this, capacitance is always going to be proportional to the plate area and always inversely proportional between the distance between the plates. You all see that right there? For a parallel plate capacitor. Now, the neat thing about this one is I worked it in reverse because I wanted to showcase the fact that charge density was equal to the D normal. That's an important concept to grasp and make sure you understand. With me on this? Okay, last couple of things. All right, one thing. I did not look at this. I should know this, but I don't. When is our last home basketball game?
I want to say it's this Saturday. Yeah,
Anybody?
it's this Saturday against South Carolina.
This Saturday?
Yeah.
Okay. So, has anybody in here bought March Madness tickets or any of these things that are available?
Not yet.
Alright, when you guys start buying them, let me know. Because I've got to figure out who's going to be here and who's not going to be here and when. I'm telling you, what, 3 years ago, was it? When we were in the tournament?
Yeah. It's 2019.
Boy, I don't expect many people to show up once they get into the round of 8. I'm telling you, if they can, they're going to be gone. I love basketball, but I ain't going nowhere. I think what they do is incentivize. They put all these tickets on sale. You get this, you know, you're going to get a hotel, you're going to get everything. It's going to be basically free, which is a lot. Then when you're out there, you're paying for everything else they didn't tell you about. Remember what I'm saying? Okay. Now I'm going to talk about energy density. So, this is something a lot of people don't really comprehend, but, you know, in the air right here, you've got power flowing, right? Electromagnetic waves are flowing. You also have something called electrostatic energy here that can be, believe it or not, around a capacitor, especially you can get that back. You can get it out of a capacitor. So the energy density in an electric field, and this is the energy density, the symbol we use is small w sub e, but don't worry about the symbol. This is energy density, and it's equal to, and this is electrostatic, I better put. Electrostatic energy density. I'm not going to prove this. In the higher level courses, we go through a formal proof on this. 1/2, and it's times E dot D, or it's 1/2 epsilon times magnitude of E squared. Either one's true. Now, this is an important concept, all right? Energy density. Well, energy is in joules. Density means it's per meter cubed. Follow me? Joules per meter cubed. That's electrostatic energy density. So if you want to find out how much energy is in a region, you would integrate the electrostatic energy density over the volume. And that should make perfect sense to you. Do y'all agree with that? And once you have that, you can also, we'll do this, the total energy in electrostatic energy is going to be the integral of the energy density over any volume. That's the total energy. But we can get capacitance by knowing 1/2 CV squared. Remember, I'd say the voltage in this equation is equal to the voltage difference between the plates, would be equal to that energy, or the integral of epsilon over 2 times magnitude of E squared over the volume. And we can integrate the energy density over the volume of space that it exists in, and then equate it to 1/2 V squared times C, and really solve for C here. And the only way you're going to see this is if I do it, so I'm going to do it. I'm going to try to do it for a very simple problem. Just follow me on this. Remember how we just had this problem where we had capacitor plates area A and A, and we had a dimension H between them and some epsilon in between. And what I did is put a voltage V0 here, didn't I? Right? Well, this is plus to minus V0. Y'all remember that? And we saw the capacitance here was equal to 1/2, capacitance was equal to epsilon A divided by H, right? So the energy, just from this form of the energy calculation, the energy in that capacitor would be equal to 1/2 CV squared, or it's 1/2 epsilon A over H times V squared. Y'all with me? I'm just putting down what it's equated, right? Whatever V is, that should be the energy. Now, we got the capacitance before by assuming the voltage, then getting the E field, then getting D, finally rho S, then the charge, and saying capacitance was Q over V. Now what we're going to do is calculate the energy density first. So the energy density would be equal to 1/2 epsilon times E squared. Well, E is V over H, right? Remember, for that problem, it's V naught over H squared. That would be the energy density. Do y'all agree with me with that? Just take 1/2 times epsilon times V times the E field, which is V over H squared, right? All right, now I'm going to integrate that over the volume. Well, when I integrate this energy density over the volume, I'm really integrating it over the internal volume of that rectangle, correct, class? Y'all follow me? What's that going to be? Does the energy density change versus position? Let me try that. Not at all, right? So I'm really taking energy density integrated over volume is what? Is just the energy density integrating the differential volume, integrated differential volume, you get the volume. Y'all follow me on that, class? And the volume of a rectangular or something with dimensions of length, width, and height is what? Well, it's just the length times the width, or A, right? Times the height, H. Or I can say that total energy is equal to the energy density that's this, times A times H. And that's equal to 1/2 C V naught squared. Now, do y'all see what I've done there? I've started, I used the E field that I got by assuming a voltage, and now I'm calculating the total energy in that system. And I'm going to get the capacitance this way. Now, y'all see that V naught squared cancels, don't you, class? I'm over by 2 minutes. I owe you 2 minutes. I'll figure out a way to make it up. Then I'm going to get rid of the 1/2, right? And, well, that 1 squared won't bother me, but I've got H squared downstairs and H upstairs, so it's really just 1 over H, right? And there it is, epsilon A over H is the capacitance as it was from our prior calculation. You can get it with either calculation, either energy density, or by doing assume Q, or in that case assume V, get E, from E, get D, from D, get rho S, from rho S, get Q, and going backwards. Now, on Wednesday I'm going to give you some homework. Please do it this time. And do the prior homework. Make sure you're aware, because I want to go through what's going to be on the quiz on Friday. Then you're gone for a week. It should be back there.
Yeah.